Okay, topic 9, electric fields. First aspect that we want to just have a bit of a look at is electric charge. Electric charge is one of these fundamental sort of quantities in nature. We could just say under this heading that charge is carried by protons. That's going to be positive charge, and electrons, and that's going to be negative charge. So minus VE for negative for short, plus PE short for positive there. So I said it's a fundamental quantity in nature. And is defined in terms of electric current. And that's because electric current is more easy to measure directly than electric charge. Alright, so what do we mean, first of all, by electric current? Alright, so we've got a diagram over here on the right that's showing a conductor. I do note that it's got both positive and negative charges moving. Generally speaking, it would be the negative electrons that are doing the moving when we have an electric current. So what's an electric current? A current is a flow of charged particles. Usually electrons in a wire. Or conductor. Okay, so definition of charge. I'll start the definition off, and I want you to complete it by looking up page 40 of your dictionary. All right, so you'll find on page 40, talks about charge, and it says charge passing a point equals and I want you to complete that particular statement there. All right, the Coulomb. So you're told in the learning outcomes that you need to be able to define electric charge and also to define the Coulomb. Well, the Coulomb is the SI unit of charge, and in terms of a definition, this comes from the dictionary too, a Coulomb is the amount of charge flowing per second past the point in a circuit in which the current is 1, should use little a, 1 ampere. All right, so in terms of the formula, well, that's represented by the statement Q equals IT. Q is electric charge. I is electric current. And T is time in seconds. Need to remember that, seconds. Right, so here's an example which I want you to copy into your notes. I just take note of the fact that the first part of the question talks about 12 minutes, so we need to change that time to seconds. So you work out the charge in part A of this question, and then you need to work out the number of electrons. To do that, you need to know that the charge on one electron, represented by the symbol little e, is 1.60 times 10 to the negative 19 coulombs. So using that, you should be able to figure out the number of electrons. That's where you write your answers. Okay, the law of charges. Like charges do something or other, or like charges repel. So just going to be a little bit careful here. This top statement here, of course, refers to that diagram down there, and unlike charges attract, and that refers to that diagram up here. And in terms of repulsion, it could just as easily be two lots of negative charges that repel as opposed to two lots of positive charges that are shown in that diagram there. Testing for the law of charges, you do not need to put this into your notes. Okay, we've looked at this in class, but the idea of two rods made of the same material, then repelling, both negatively charged, two rods of different materials, therefore attracting positive and negative charges there. Okay, induction, not something that the syllabus specifically mentions, so we're just going to mention this in passing. Nothing here that you need to write in your notes books. The electroscope is this device here. It's a device used for detecting the presence of electric charge. So what we've done here, this rod is brought near the electroscope without actually touching it. When it's brought near the electroscope, the positive charge on the rod draws these electrons to the top of the electroscope, leaving positive charge behind. So we have induced, hence the word induction, we have induced charge separation. Overall, the electroscope should still be in neutral, uncharged. It's just we've separated the charges. If you look carefully at the diagram here, I don't think it is perfectly drawn in that really there should be an equal number of negatives there compared to the number of positives down on the bottom part of the electroscope. If we look at the next diagram, just a little bit more, just showing electroscope. So on this left-hand diagram here, we've got an electroscope that is negatively charged. These negative charges here all want to get as far away from each other as possible, so they spread themselves out evenly over the whole electroscope. This part here is a piece of gold leaf, which is nice and thin and light, and so because like charges repel, the electroscope leaf goes up. If that electroscope on the left-hand side is then connected to Earth, so let's say we connect it to Earth, that's the symbol for Earth, what's going to happen is that the electrons are going to flow down to Earth, and so you'll end up with the electroscope being uncharged and that leaf has collapsed there. Let's have a look at a couple of applications of basic sort of electrostatics. The first one in terms of spray painting. For example, it could be in a spray painting booth painting a car, and this is what's actually done in reality. Let's say that this spray nozzle is negatively charged and the thing being painted is positively charged. The paint, as it exits the nozzle, picks up charge from the nozzle, and so you end up with all these little paint droplets, all that are negatively charged, being attracted to the positively charged surface. So if it was a paint or spray booth for a car that's been manufactured, the car will actually be connected out the body of the car connected to a circuit and the paint sprayed onto it. So that rather than simply relying on gravity, causing the droplets to fall onto the car, you've got the droplets actually being attracted to the vehicle instead, just giving a much more precise and complete paint job. A couple of other little illustrations here. Dust extraction down the bottom is a filter, an air filter, I think, again, effectively extracting stuff from the air. This thing up here, some sort of extractor type device. Basically what it works like is if you've got a grid, I'm looking down on top of this grid here, and if this grid is charged, we've seen in class how neutral objects like a little piece of paper is attracted to a Van de Graaff generator. Same sort of thing here. You connect this grid to a high voltage, and as the dust particles try to pass through the grid, they are attracted to the grid and therefore cleaned out of the air, so that the air that exits from this stack, this chimney stack, is effectively cleansed of that dust.